Before I labeled the DEPT spectrum, the distortionless enhanced bipolarization transfer spectrum, I'm going to look at the 1D NMR and use the same signal numbers that I used for 1D in the 2D DEPT spectra. This one, we have 8 total carbons, if you remember. Let me circle them for us. Let's see. So we have a carbonyl for the acid. That's signal number 1 right here, right? The most downfield. And then we have these aromatics. They're all unique. 1, 2, 3, 4, 5, 6 signals. And we do see 6 signals in the aromatic region because it's 2 through 7. And there's a couple we can kind of get. So the carbons with no hydrogens, this one, that's going to be either signal 2 or 6 because carbons without hydrogens tend to be shorter. And then the other one here is also going to be 2 or 6. Let me make a guess at it. Let me see. 1, 2, 2. Yeah, I'm not sure. Yeah, those ones are close. I don't know. Wait, no. I think this one's going to be, my guess is this one will be 2. So I'll put 2 or 6 here. 6 or 2 there. And you can look it up, see if I'm right on SDBS. Okay, and then these other ones, let's call these ones X, all these other aromatic carbons, they all have a single hydrogen on them. And we'll say X is either 3 or 4 or 5 or 7. So it's one of those ones. And then the methyl is, of course, 8. Okay, so we're going to use those same numbers. When we look at the DEPT spectra, you're going to notice that carbons without hydrogens don't show up in any of the 3 spectra on a DEPT. So carbons without hydrogens would be signal 1. This should not be on the DEPT. And then 2 or 6, they shouldn't be on the DEPT. So when we go over there, I don't want to call the first signal I see, which is 3 here, I don't want to call that 1. I want to still call it 3. I want to have the same numbers through all the spectra. So let's move over to that DEPT spectrum. So we are missing signals 1 and 2. And what we have here is signals 3. Oops. 3. I'm going to zoom in on it. Okay. 3. Oh, it changed colors on me when I zoomed in. Okay, finally. 3, 4, 5. We're missing 6, and this is 7. And so this again is 3, 4, 5 here and 7. 3, 4, 5 here and 7. And then obviously the one out here in the alkane region is 8. It's showing up on the top spectra, but not the bottom, not the middle spectrum, top and bottom. So let's talk more about what's going on with these spectra. These are kind of crazy, huh? In the DEPT 35, the carbons without hydrogens, so CH0, the quaternary carbons, they just don't show up. You will not see them. That's why we're not seeing our carbonyl. We're not seeing signal 2 or the signal 6 that was in there because they have no hydrogens. And carbons with 1 hydrogen and carbons with 3 hydrogens, they have signals pointing upward. So all these are, if we only have this DEPT 35 spectra to go by, we would say all of these signals 3, 4, 5, 7, 8, they either have 1 hydrogen or 3 hydrogens, an odd number of hydrogens. Something interesting that we don't happen to have in this molecule is if you have a on this spectra, if you have an even number of hydrogens on your carbon, a CH2, then your signal would point down. So it would be like, you'd see a signal pointing down, you'd know right away, oh, that's a CH2. But we don't have any CH2s on this molecule. Now the next spectra, the depth 90, the middle one, this one will just only show CHs. CH1, they have signals pointing up. But the CH0, CH2, CH3, they don't show up at all. So this is nice because now when I only had this top depth 35 to go by, all I could say at this point was that 3, 4, 5, 7 could be a CH1 or a CH3. But since they're showing up here on the one that only has CH1s, I know that, oh, all these are all CH1s. CH1. Okay, now hopefully this will start to make even more sense with 8. So signal 8, when I'm looking at the depth 135, it tells me that it's pointing up. It's either a CH1 or a CH2. When I come to the depth 90, it's no longer present. That means that, oh, it's not a CH1 because only CH1s show up. So it's gone, so not CH1. This must be a CH3, and that should make sense to us too because we know we have the methyl on our ortho-toluic acid. That's going to show up in this 20 parts per million range, between 50 and 0 here, and it has 3 hydrogens, so nice, huh? Okay, and then this last spectra, it's kind of redundant, the depth 45, because it shows CH0s don't show up again, but it shows everybody else, CH1, CH1, CH, sorry, I'm getting sloppy here. CH1, comma, CH2, comma, CH3, point upward. So these are all showing up the same, 3 signals, 3 through 5. Oh, I put 4 there, 3 through 5 and 7. And then the CH shows up again because the CH3s do show up on this one. Okay, so we got that. So let's go ahead and now try to label this again. I have a set of rules on how I like you to label depth spectras, but this is our first time looking at them. I'm just going to do it for you. So we already know this one here, the carbonyl is signal 1 because it's the most downfield. It's not showing up on this spectra because it has no hydrogens. And this is signal 8. It makes sense because it's a CH. It's the only alkyl signal, and it has 3 hydrogens. 3 hydrogens, looking good. And then these 2 have no hydrogens on them. They're not showing up on this spectra, so these are, I said it's 6 or 2, and this one is 2 or 6. All right, and then we've got these other ones. We'll call those X, and those are the ones that are CHs, all these CHs here. So those again are X equals 3 or 4 or 5 or 7. Okay, so I got that labeled. Now I want to fill in my depth table. What I do for the depth table, I just came up with a way to make you, process this data well. This is just my table I made up. So what I want to do is I want to say signal 1. How many hydrogens should it have? Theoretically, looking at the structure, signal 1 should have 0 hydrogens. And then according to, I'm sorry, I'm doing this backwards. This is supposed to be from the depth data. From the depth data, signal 1 didn't show up, so it's 0 hydrogens. On our structure, it also says 0 hydrogens, so it agrees. And now signal 2, I'm saying signal 2 is one of these, and it's the one that's missing. So that should be 0 hydrogens, and our structure, we're predicting 0 hydrogens. So now signal 3, that's one of these X's. So these are supposed to have a single hydrogen. So I'm expecting one hydrogen for signal 3. And signal 3 is showing up on this one, which says it's CH1 or CH3, and it's also showing up on this one, which means it's CH1. So it's agreeing perfectly. One hydrogen, looking good. Signal 4 is the same thing. It's one of these X's, and it's showing up. So one hydrogen. Signal 5, also one of the X's, one H, it looks good. Signal 6 is missing. So signal 6 looks like it's 0 hydrogens. And on our spectra, I'm predicting that one to be signal 6, 0 hydrogens. So it's looking perfect. And then signal 7 is a CH. So one hydrogen, and we predict it to be one hydrogen too, because we predicted it in here to be one of these CHs. Finally, signal 8 is it looks to be a CH3 because it shows up here but not there. So we're thinking 3 hydrogens, and on our structure we're saying it's the 3 hydrogen methyl, so it agrees perfectly. So it's a perfect match. Looks good. So in the future, I'll have you do that kind of labeling on your own, but I thought this time I'd go through it. Hopefully it makes more sense.